Hi AP Calcers. We're going to start into Chapter 5 here today, and you might have heard me mention some things about the two branches of calculus. Up to this point we've looked at the first branch, which we called differential calculus, and of course the main idea with that was this thing called the derivative. And of course, when we first did the derivative, the key idea there was that it was just a different form of slope. And of course, we did several problems with that. We saw many uses of it, and just all around good stuff that we did. Now, the second branch, which we start in this unit, is called integral calculus. And I think we might have mentioned this before, but we'll just review it once again. It's like a topic that you've studied for quite a while now in your mathematical career, and that is area. And specifically what we're going to look at in terms of area with the integral is area under a curve. I don't know, I might have goofed this up a little bit how I wanted to say it, but area under a curve. Alright? And so that's what we're going to be focusing on this next segment of the class. I'm not sure what all those extra slides got in there for, but here we are, area under a curve. Now, you've done a lot of work with area, but I would venture to guess you've never been able to find an area such as this. And after a little while we'll be able to do that. We'll be able to actually find a real specific value for the area under this curve. And we'll gradually get to that point, but that's one of the real cool things about calculus, is being able to do that. Alright, so we're going to first of all focus today on the area under a curve, but we're going to find that using rectangles. So I think you would agree that even though this is a curvy surface here, if I made a bunch of rectangles, I know how to find the area of a rectangle fairly easily, length times width. If I put a bunch of rectangles under a curve, I could get a decent approximation for what that area is under that curve. Would it be perfect? No. We can already see there's some spaces here where that would be missed, but then there's some extra area here. So if we found the area of all these rectangles, one would think that it would be a fairly close approximation, but not perfect. Here's an example of finding the area under a curve using rectangles, but notice it does depend upon the endpoints. And we're always looking from the area from A to B, and it always looks like these rectangles are the same width, but notice it does matter how we draw these rectangles whether we use the left endpoint, so all the left ones hit the curve as far as their y values, or the right endpoint, where all the right ends hit the curve that we're trying to find the area underneath, or even something called the midpoint. I think you can see that even though we have the same function and we're trying to find the area over that same interval, each of these would be a little bit different because of the endpoints that are being used. Anyway, we're going to use a particular program on your calculators, and you may not have gotten that loaded yet in class. We'll make sure to do that the next time we have class. There's a nice program on it that we can load on the calculators called the RAM program. RAM stands for rectangle approximation measurement or something like that, I think, and there we'll be able to use it to estimate. Now let's just say we have this particular function, y equals x squared minus 4, a parabola that's been shifted down a little bit. We'd like to find that area between that graph and the x-axis. That's typical to what we'll find between 0 and 5. 0 and 5. Now one nice thing you could do is just enter that function in your calculator and take a look at the table. and we'd be able to see some y values. Notice when x is 0, y is -4. We could make a little rectangle underneath there like that. When x is 1, y is -3, so we can make another little rectangle, and so on and so forth. We'd be able to figure out the areas by adding up these particular y values in a sense, and that would be one way to be able to get our area. Now, just to show you some screens of what this will look like on your calculator when we do them, we have this program that we'll get on there called the RAM program. Now, all these weird words, LRAM, RRAM, MRAM, stand for using the left endpoint, the right endpoint, the midpoint. These next three we'll talk about in later lessons. These are just some other ways that we will use to approximate area. Anyway, if I select the right endpoint, the RRAM, then it'll ask me to put in the equation of the function, which I did, the left bound and right bound. In this case, it's from 0 to 5. The number of rectangles, here we said there'll just be 5 rectangles, and then basically it will calculate that area for us. Notice in this case it's about 35. There'll be some problems on our assignment that will ask us to estimate that area using these RAM programs, and we'll try to use that LRAM and RRAM and MRAM, and we'll see the difference between them. And then finally it will do a graph like this. Now this is not rectangles that are being graphed, unfortunately, but it does give you some idea of what that area actually looks like. And believe it or not, we'll talk about this more in class, that if we have area that's underneath the x-axis like this, it's considered to be negative area. This much would be positive, it's above the x-axis, but area underneath is negative. Seems kind of strange. Alright, one last example we're going to look at. If we're going to try to find the volume of this nose cone right here by revolving the curve y equals the square root of x, which is about what that function looks like, and we're going to revolve that around, we would say the x-axis perhaps, so we'd be revolving that around there from x equals 2 to x equals 10, and then we'd partition this into 4 intervals. In other words, 4 big cylinders, so to speak. And then if we could find the area of each of those cylinders, the volume of each of those cylinders, and then add them up, that would be a good approximation for the volume of this whole nose cone. And we'd like to use the left endpoints. Now let's think about this a little bit here. See if I can get a nice color. We would agree, I would think, that the volume of a cylinder is the area of the base. So if we think about it, it's going to be a circular base. There's pi r squared. And then we'd have to have the height of that particular cylinder. So that's a fairly familiar volume formula. Now, picture this, that another name for the radius here, if we kind of look at this from the side, the radius would look like this, but the radius is really going to be that equation of y here. That's going to be the same as the radius, because as you go along this point here, your radius is going to be changing. It'll be getting a little bit bigger. And so I'll be able to actually put this value here, that square root of x, in place of that radius. Now it seems a little bit strange. So I'm going to put pi here. The radius is the square root of x, but I'm squaring it. And then here's height. Now the square root of x squared is just going to be x. So basically I'm going to get a little equation that looks like this. Now keep in mind that the height of each of these little cylinders that I'm trying to produce here, the height of each one I think is going to be 2, because I'm going to try to do 4 intervals between here and here, so I think each one is going to be 2. So that means when I use this RAM program, and here's where it's kind of strange, the RAM program, and especially those intervals, those 4 intervals between 2 and 10, in a sense that takes up this height here. Those account for that height. So notice when I go to my RAM program, I'm Again, that tells us, the problem tells us to use left endpoint, so that's why I choose this LRAM. Notice what I put in there for the equation, just pi times x. I don't put anything in there at all for height because the rectangles and the width of each rectangle will essentially account for the height. So my bounds are from 2 to 10. That's what it says right here. Number of rectangles is 4 because I want each one to be 2, width of 2. And sure enough, here's my area right here. There's my area. Now again, it would be different, of course, if I used the RRAM or MRAM. But again, just showing you, kind of getting started for a feel for how we can calculate some areas and volumes simply by approximating using either rectangles, or in our case here, we're doing cylinders. Alright, thanks for watching, everybody, and we'll see you guys in class.